Good morning, everyone.
Hi, good morning.
How are you doing?
Very well.
Excellent.
Yeah.
So you got the set of problems for chapter 3.
Yeah.
I emailed them Tuesday. Okay, work on them because that's really going to prepare you for the exam as well. Okay, and then there's going to be another set for chapter 3 that includes a spherical coordinate and the materials I'm teaching today. And I will assign them after the midterm. And then you're going to do that and prepare for the quiz for that part of the chapter 3. Okay, so we will talk more about that after the midterm. Okay, so what I'm going to do today, I'm going to continue chapter 3. I'm going to talk about the dipoles. I'm going to talk about physical dipoles, calculate electric potential and electric fields of a dipole. And then we're going to look at on how we can approximate the potential at large distances created by a random distribution of charges. We're going to expand that Taylor expansion type of approximation, and we're going to look at the monopole and dipole terms. And then hopefully I have time to give you a bit of introduction on chapter 4, which is actually related to the dipoles and some of the discussion on chapter 3. So there's a good flow from end of chapter 3 to chapter 4. Okay, so question, what is a dipole? What is an electric dipole? If you have one single charge, positive or negative, that is basically one single charge. It's often called as monopole. Right. If you have two charges, which is one step more complicated than monopole, you have one positive and negative charges, and this is often called a dipole. Okay, so this is basically the way I said it. If you put charge of positive Q on the top one and negative Q on the bottom one, and if they are separated by distance D, D itself can be a vector. Okay, this is called a physical dipole. Okay. Give me 1 minute. Okay, so this is called a physical dipole. The distance D and charges on each side is positive and negative of Q. Okay, so this quantity P defined as Q times D is often called dipole moment. It has magnitude and direction as well. It's a vector, okay? And the direction is direction from negative to positive charge. And the magnitude depends on the distance and also the charge you put on the dipole, okay? So the fact that these are positive and negative charges, if they are close to each other, and if you look at them from far distance, the distance between the two charges could be small compared to where we are, okay? So at large distances, we can approximate the potential created by these two charges. Okay, imagine we are sitting at distance r, and r is much greater, much bigger than d. Okay, if we do that, this angle theta, okay, depending on the angle theta, we can calculate the potential of this. Okay, so without approximation, the potential at this point, V of r, is basically is a potential created by this positive and this negative charge. We have the distance from the positive point to the r as r plus, and let's assume the distance from the negative charge to this point is R minus. Okay, so basically the way the potential is created at this point is just adding up the potential created by this positive and negative charge. Mathematically, it has simple form. V of R is 1 over 4 pi epsilon naught times Q divided by R plus minus Q divided by R minus. This negative sign because the charge here is negative Q, and so we have the same Q over R plus, Q over R minus, okay? So now we can look at what is R plus and what is R minus, okay? Basically, you can write R plus and R minus in as a function of R, the distance to the center here, and as a function of theta, okay? So if we use cosine rule, we can write R plus to the power of 2 is R2 plus d by 2 to the power of 2 minus RD cosine theta. Sounds good? For R minus, very similar. If we use R minus, here we have R2, again we have plus D over 2 square. Here we have minus because the D is actually the other side. Okay, so R plus minus can be written in an accurate way in terms of the R, D by 2, and cosine theta. Sounds good? Okay, so basically we need to just plug back this R plus and R minus here to calculate VR. But you can imagine if you put the whole term, 3 terms here in the denominator, it's not going to look easy. Okay, so if R, the distance we are here, is far from this dipole, then we can do some approximation because the term D is much smaller than R. Okay, so this term becomes small, and this term, R by D, is kind of small as well. Okay, so let's move on. I'm going to look at 1 over R plus and 1 over R minus, and I'm going to see how we can approximate that. So by approximation, I mean we're going to expand it, we're going to make a Taylor expansion and keep the first term and the second term. Okay, so any term that contains D over R to the power of 2, I want to assume that this term is way too small and drop that. Okay, so that's the approximation I want to do. Okay, so if we look at 1 over R, okay, R plus or minus, this is going to be equal to 1 over R, so I'm taking R out of this. Okay, so basically what I'm doing is, let me get rid of this now. I'm writing this in terms of, so if we pull out R squared here, we get 1 plus D by 2R to the power of 2 minus plus D over R cosine theta. Okay, so if you pull out R, you're gonna get this one. And then the rest are the D over R terms that you have in the second and third. Okay, so now if you look at 1 over R plus minus, you get 1 over R, okay, and you get 1 plus D over R to R to the power of 2 minus plus D over R cos theta to the power of negative 1/2. Okay, so I inverted this one, I inverted 1. So this one is going to be 1 over R. Okay, so the terms we have here is 1 plus d over r square minus plus d over r cosine theta to the power of 1/2, negative 1/2. Okay. Now, if you look at this term has d over r square. Okay, we're gonna make the assumption that this term is too small. We're gonna get rid of this. Okay. So then here we get negative plus d over r cosine theta to the power of 1/2. Okay. Now, if you expand it, this is going to be, if you expand it and if you keep the first term, it's going to be 1 over r times 1 minus plus, okay, actually plus minus, one half d over r cosine theta. Okay, so I did one approximation here. I got rid of d square over r square, and then we have the whole term here to the power of negative 1/2. And if if you have 1 plus epsilon to the power of negative 1/2, okay, if you expand it and only keep the first term, you get 1 minus 1/2 times epsilon. Okay, so I did similar type of thing. Imagine the whole thing here is epsilon. And then here we get 1 over r, 1 plus minus 1/2 d over r cosine theta. Okay, so this is how we can approximate 1 over r plus minus, okay, if we are far from the dipole. Okay, now what we want to look at is this term. We can actually pull the factor q out here, okay, and what we have in the parentheses is 1 over r plus minus minus 1 over r minus. Okay, so if we want to use this and look at 1 over r plus minus 1 over r minus, what do we get is we have 1 over factors canceling each other out, and we get 1/2 d over r cosine theta minus 1/2 d over r cosine theta. That becomes d over r cosine theta. Sounds good? So the whole thing here is the terms in the bracket here, and that kind of simplifies to d over r cosine theta. Again, this is an approximation, and this is when r is much bigger than d in a way that we can get rid of, we can neglect all the d over r to the power of 2 terms. Sounds good? Any question? Is it clear what approximation we invoked on the way to this point? Yes? Sounds good. Okay, so now with all this approximation at the end, if we want to look at the potential, let me get rid of this. The V at R can be approximated as Q over 4 pi epsilon 0 times D over R cosine theta. Okay, so now if you look at the numerator here, I can rewrite it in a different form. I can say 1 over 4 pi epsilon 0. Here we have QD cosine theta over R. Okay, so I'm going to rewrite it in just a different form. Okay, what is the angle theta? Theta is here. What is cosine theta? Okay, so theta is the angle between P, the dipole moment, and R, the position at which we are calculating the potential at, right? So if you look at P dot R, what you get is QD, which is a magnitude of P, times R, which is magnitude of distance, times cosine theta. Okay, so QD cosine theta is technically P dot R divided by the magnitude of R. So this is basically, if I divide both sides by R, we get this, and we get QD cosine theta. Okay, so what is R divided by magnitude of R? That's basically R hat. So P dot R hat is QD cosine theta. Sounds good? So I'm just trying to rewrite this numerator in terms of the dipole moment and the radius we have here, so that the cosine theta is not direct and obvious here. So this can be rewritten as P, the dipole moment, times R hat. Sounds good? So if in one direction you move away, the potential decreases as a function of 1 over R. By the way, let me double check something. So in the approximation here, we get R square actually. Okay, so this should be R square, and here we get R square. Sounds good? So the potential is P dot R hat divided by R square. And this is the potential of a physical dipole far from the dipole. Okay, and here when I say physical dipole, the reason is that there are different ways you can define a dipole. If you have a dipole that are created by 2-point charges being positive and negative, exactly the same magnitude, that's called physical dipole. You can create different type of dipoles by having different ways of charge distribution, not necessarily positive and negative exactly. Okay, so there are different type of dipoles. But this is the most basic and clear way of defining a dipole. Sounds good? Any question? Everything more or less clear here?
So is this equation the same as the one we got for the one you erased?
Can you repeat the question?
So this equation that we got with the V of R, and we substituted in the P R hat. Is that this? What's the difference between that and the equation when we had the 1 over R plus minus equals 1 over R times the parentheses?
I'm not sure. Compared to this one?
Yeah, you know how we worked with that one first and we approximated it?
Yes.
At the end?
So we started from here, and this is an approximate. So technically, I should put this and this here. Okay. So if you are far from the dipole, these can be approximated by this term.
Okay.
Okay. And here I just QD cosine theta. I wrote it in terms of the dipole moment dot R hat.
Okay.
So these two terms are identical. Okay, but these two are not identical. This is an approximation. And this approximation is pretty useful. Sounds good? Any more question? Okay, so So something special about this is how the potential decays as a function of R. Okay, so if we get rid of this, when we had a monopole, one single point charge, the potential as a function of R decays in the form of 1 over R. Okay, and then if you have dipole, negative and positive, the potential decays as a function of 1 over R squared. Okay, and what you can do, in fact, you can use two dipoles and put them next to each other upside down, and you can have a higher order system, and this is called quadrupole. Okay, the potential of these decays as a function of 1 over R3. Okay, so these are higher order terms that you can create with positive and negative charges. The first one is monopole. You either have positive or negative charge. Potential decays as 1 over R. Dipole means you have two opposite charges putting very close to each other. Potential decays as 1 over R squared. Quadrupole is basically two dipoles that you put upside down next to each other, the way that positive and negative charges are neighboring each other. And if you calculate the potential of this and approximate this, it drops as a function of R1 over R cubed. Okay. And basically, you can go one step forward. You can put two quadrupoles side by side in a way that they form something like a cube. So you have positive and negative charge, and then you have negative and positive charge. If you put two of them next to each other, they form a cube that you have all these positive and negative charges neighboring each other. And this is actually called octupole. And if you look at the potential of this, it decays as a function of 1 over 4 cube. Okay, and now you can imagine if you are going further and further away from each of these ones, R is increasing, and the way the behavior is as a function of R, they drop faster and faster. Okay, 1 over R squared drops faster than 1 over R. 1 over R cubed drops faster than 1 over R squared, and so on. Okay, so in terms of calculating potential and electric field, we just look at the dipole. These terms can be a little more complicated. Okay, we are not calculating that, but I'm just giving you the information on so that you have some insight on how you can arrange positive and negative charges to create higher order terms. Sounds good? So what we calculated here is this potential that V drops as a function of 1 over R squared. Sounds good? Any question? Is it clear more or less? Okay. So what I want to do next is that I want to start from this potential, or this one, identical, doesn't matter, and I want to calculate the electric field created by a dipole. Okay, so potential of a dipole, V of R, I'm just rewriting that one, is 1 over 4 pi epsilon 0. Q the cosine theta divided by R, which is equal to 1 over 4 pi epsilon 0. P dot R hat. This is R squared, and this is R squared. Okay. Now the question is, if we have this potential, electric potential from the dipole, what is the electric field we get out of from that? Okay, so electric field is the negative of the gradient of the potential. Okay, so here basically the system that we use a spherical coordinates, we use r and theta, and the assumption was that P is sitting in the z hat direction. Okay, so this is the vector P. The electric dipole, okay, so if this is X, Y, and Z. Okay. So this is P, and imagine we are at position R here. Okay. So this is basically the coordinates that is, and this is P. Okay. So this equation in here gives us the potential at this point. P is in the Z hat direction, and theta is the direction between R and P, like this. Okay, so if this is the coordinate system, we should take the gradient in a spherical coordinate as well. So we're gonna look at the electric field in terms of the components ER, E theta, and E phi. Okay, so the R component is the negative of derivative of V respect to R. The theta component is negative 1 over R partial V partial theta, and the phi is 1 over R sine theta. Okay, of course we have a negative sign as well, times dV over d phi. Okay, so we need to calculate these three electric field components. Okay, now if you look at the first term, dV over dr, okay, that's going to be two QD cosine theta times 4 pi epsilon 0 r to the power of 3. So basically, the r dependence is 1 over r squared. You take the derivative of this, you get r cubed in the denominator. The negative sign cancels out with this negative sign. You get 2 here, so you get 2 QD cosine theta in the numerator and 4 pi epsilon 0 times r cubed in the denominator. Okay. So for E theta, we are taking derivative with respect to theta here. We have a negative sign here. So what we get is the term QD times sine theta, derivative of cosine is negative sign, again cancels out with this negative sign, 4 pi epsilon 0. We have r squared, we have 1 over r here, combined it becomes 1 over r3. Okay. And then if you look at the phi dependence, there's no phi dependence in VR, so this term just becomes 0. Okay, so the electric field components, we just get two components, one in r hat direction, the other one in theta hat direction. Okay, so combining everything, okay, the electric field as a whole, we can write it in terms of QD divided by 4 pi epsilon 0 r cubed. Okay, so we have 4 pi epsilon 0 r cubed from these terms times the first term is in the direction of r hat. Okay, so we get 2 cosine theta r hat plus sine theta theta. And again, there is no phi dependence. Sounds good? So what we did, we just simply looked at the gradient and we look at the component, 3 components in a spherical coordinates. There is no phi dependence. One of them is simply 0, and then just we took the derivative to calculate the 2 other components as well. Sounds good? Is this more or less clear?
Yeah, Professor, on the graph you drew, the bottom line, is that a projection on the XY plane?
This is a projection on the XY plane. So basically, this is phi, okay?
Okay.
And this vector here is the P.
Thank you.
Sounds good. Any more question? So next, what I want to do, I want to plot this for you so you have a physical sense of how the component, how the electric field lines look like on a diagram.
And this is all still for dipoles, right?
All this stuff are for dipoles, yes.
Okay.
So what we did first, we calculated electric potential, and then now we calculated electric field. Okay. So if you look at E, it's in the direction of R hat and theta hat only, there's no phi dependence. So what I want to do is that I want to plot this in ZY plane. Okay, and imagine the dipole is sitting here, the positive charge is up, okay, and the way the field lines look like, they are like this. Okay. And I guess this is familiar for you. This is exactly the way the field lines of a magnet, which is basically a magnetic dipole, look like. Okay, the positive side, negative side, and you have field lines circulating from the positive to negative, positive to negative. Okay, and as you go further away, the magnitude of force drops, but the field lines becomes bigger and bigger. Looks good? Yes? Okay. Okay, so what I want to do next is, so we are done with the dipoles. What I want to do is that I'm going to look at, let's say, a random distribution of charges. Okay, I want to look at the random distribution of charges and start by calculating potential as an integral of all small charges, okay, integral over the volume of that random charge distribution. And then I want to try to expand that in the exponent in terms of 1 over r. Okay, so I want to have a leading term, a second order term, and third order term, and so on. Okay, and then I want to define the dipole, magnetic electric dipole, as a function of the way we do this expansion. Okay, and and basically that's going to be a Taylor expansion in terms of 1 over. Okay, so let me start doing that and then we go step by step. Any question on the dipole here? Everything clear more or less? Okay. So again, I'm not getting many questions, and sometimes it means it's clear, sometimes it means so confusing that no one can even ask a question. Hopefully the first case is true now. Okay. So now let's consider here we have a random charge distribution, and the charge density at any point, let's say we choose any small volume here, let's assume the charge density here is rho r prime, okay? And let's imagine that we are trying to calculate the electric potential. Let's make it a bit bigger, it makes sense. Electric potential at distance r, which is large compared to the length scale of this charge distribution. Okay, and that means if we look at this, let's say infinitesimal volume, d tau prime, okay, which sits at the position r prime, okay. So we have this charge distribution, and one way to calculate electric potential here is one integration over all these infinitesimal volumes. Okay, so the potential in terms of integral is 1 over 4 pi epsilon 0 integral of rho r prime, which is charge density at this point, times d tau prime, which is infinitesimal volume here, divided by r, which is a distance vector from this point to where we are calculating potential. So something like this, and this is r. Okay. So if you can do the integral here precisely, you are lucky you can calculate potential. But we did that for actually a few very special cases like a disk or a sphere or things like that. But you know, generally that's not an easy thing to calculate. Okay. So here what I want to do is that I want to write this and expand it so that we have different terms in the format of 1 over r, in terms of 1 over r. And that what I mean is this, I want to have V of r calculated as 1 over 4 pi epsilon 0 times 1 over r times something q star plus 1 over r squared something p star plus 1 over r cubed r star and so on. Okay. So I want to do this expansion, calculate r in different terms, and if r is big, the first term is going to be big, the second term is smaller and smaller and so on. Okay, so it's a meaningful expansion only if we are looking at this charge distribution from large distance, okay, not from close distance. Okay, so that's what I want to do. And after that, I want to look more carefully at the first term and second term and see how they really look. Okay, so what we need to do here is that we need to first look at this distance vector and try to expand it as a function of 1 over r. Okay. The distance vector r squared, we can use cosine rule, which is makes it r squared plus r prime squared minus 2r r prime cosine if this angle is alpha times cosine. Okay, and that can be written in terms of r squared, the rest in brackets. You get 1 plus r prime over r squared minus 2r prime over r cosine alpha. So this term, I can say that it's like epsilon because it has r prime over r terms. They are small, and that is r prime over r times r prime over r minus 2 cos alpha. Okay, and because r is big and r prime is small, this term here is a small. Okay, so r has a form of r times square root of 1 plus epsilon. Okay, so if you take the square root of this, from this side you get r, from this term you get 1r, and the whole term here is 1 plus epsilon under square root, because we took this square root. Okay. So now, if we expand this term, the whole thing here as a function of epsilon, okay, we get terms. Actually, I'm gonna skip some mathematics here. It's just expansion and expansion, okay. For the details, I let you read the textbook, okay, because it takes a lot of time to do all these terms. But at the end, we get certain terms that we can write in terms of the Legendre polynomial. Okay, so if we look at 1 over r, okay, that is equal to 1 over r times the series that you can write in terms of Legendre polynomials r prime over r times Pn of cosine alpha. Okay, of course, the first term is easy because Pn of 0 is just 1, so you get r prime over r. And then if you expand it further, the second term, you have 1 cosine alpha, okay? The first and second term are exactly similar to the terms that we had in physical dipole when I expanded, but the other terms, the higher order terms, look a little more complicated. But nice thing, everything then can be written in terms of the Legendre polynomials, and that's a nice coincidence. And the whole term here, if included all the way to infinity, really captures all the terms and becomes relatively approximation, relatively accurate way of writing 1 over r. Okay, so in this integral, you can write 1 over r in terms of this integral. Okay. Now let's put this one back here and see what we get in terms of the first term, second term, and so on. Okay, so I want to get rid of this. Okay. And I want to put this 1 over r calculated in terms of this series back in this integral. Okay, so let's continue here. We have v of r, which is 1 over 4 pi epsilon 0. Okay, and then we have the summation from 0 to infinity, 1 over, so we have, by the way, I missed the exponent n here. This is r prime over r to the power of n. Okay. So we have 1 over r here, we have 1 over r prime over r in inside this, we can take it out, and that becomes r to the power of n plus 1, okay, times the integral of r prime to the power of n Pn. So this is the first term, r to the power of n prime, Pn cos alpha, times, now the numerator here is rho r prime d theta. Okay. So what we did was we were trying to write this integral and expand it in the form of 1 over r terms, okay? And this series actually does that for us. Okay, the integral doesn't look very simple because of this Legendre polynomial term, but the nice thing is that we have all the 1 over r term outside the integral, okay? And as we go over the terms of this summation, the first term is going to give us 1 over r times something. The second term tells us 1 over r squared times something, and so on. Okay, so this actually is what you wanted to have in terms of expanding the potential in 1 over r terms. Okay, so now if you look at the first term, as I said, the Legendre polynomial for the very first term n equals 0 is simple. It's just number 1. So what we get is this. I'm trying to expand the first and second term. First, second, and third. Okay. So 1 over 4 pi epsilon 0 is what we have here. I'm going to make a big bracket open here. If we put n equals 0, here we get 1 over r. Okay. And here inside, P0 of cosine theta is just 1. The n here is 1, so we get integral of, sorry, n is 0, so r prime to the power of n is just 1. So these two terms disappear. We only get rho of r prime times d tau prime. Okay, so this is very first term that we get out of this series. 1 over r integral of rho r prime d tau prime, okay? And if you look at this, what is this? This integral over this volume, rho times volume. This integral calculates the total charge included here. Okay, so the first term looks at the whole thing like being a point charge at distance r, 1 over 4 pi epsilon 0, 1 over r times q. Okay, now let's look at the second term. Plus, I'm writing the second term here. It's going to be 1 over r squared. Here n is 1, so we get 1 over r squared here. Okay. And inside the integral, we have r prime to the power of 1, so we get r prime. Here, Pn cosine alpha, if n is 1, that's going to be equal to cosine alpha. So we get cos alpha rho r prime d tau prime. Okay, and plus 1 over r cubed times integral r prime. The next term becomes r prime to the power of 2. P2 of cosine alpha is 3 by 2 cosine alpha squared minus 1/2 times rho r prime d tau prime. And then, of course, we get higher terms down here as well. I'm not going to calculate anything more than this. Okay. So now what I want to do is that I want to again focus on the first and second term that intuitively give us something interesting. Okay, so I said the first term we get out of the whole integral is this. And the integral here, as we just said, is the total charge we have in this charge distribution. Okay, so if I want to write the first term separately, this is we are equal 1 over 4 pi epsilon 0 q divided by r. Okay, And as you can imagine, this is really like a zero order approximation. You have certain charge distribution here. You are looking at it far from this. And if you want to calculate potential in the very crude way, you just look at the whole charge included here, and you're going to say it's 1 over 4 pi epsilon 0 q divided by r. Okay, so this is the leading term in the approximation. If you look at the second term, okay, what we have is the whole term here, r prime cosine alpha times rho r prime. Okay, so there's a nice thing about it, and that is that rho prime, so r prime cos alpha, this can be written in terms of r prime as a vector times r, the distance here as a vector too. Okay, so this r, I'm writing here, r prime times cos alpha can be written as a vector r prime dot r hat. Okay, because alpha is an angle between r prime and r, so r prime cos alpha is going to be r prime dot product r hat. Okay, and now if we do this here and write this in terms of r prime dot r hat, okay, r hat itself is a constant that's independent of the d prime integration here. So that can be taken out of the integral, okay? So we can do this in the form of r hat a vector and do integral on this. And then we can have r hat out of the integral and do the dot product here. Sounds good. So here we have r prime times rho r prime beta. This I want to define it as dipole moments here. Okay, and then you're going to see why I define it as a dipole moment. So I'm going to define the vector p as the integral of r hat rho r prime rho r prime d tau prime. Okay, so if I do that, the whole term, basically the next term here becomes 1 over 4 pi epsilon 0 that we have here. Okay, times here we have r hat dot p divided by 1 over r squared. Okay. And then, of course, we have other terms as well that I don't want to calculate. So now I want you to focus on these part here. Okay. So I just look at the first and second term, and of course, there are other terms that are always smaller, getting smaller and smaller because the denominator is becoming r squared. The next term is going to be r cubed and so on. Okay, now if you look at this, the first term was very similar to the electric potential calculated by form charge. The whole charge, the total charge here, divided by r. The second term now, if you look at this, this is very similar to the potential of the physical dipole we calculated. 1 over 4 pi epsilon 0, r hat times p, right? R hat times p was exactly the form of the numerator we had when we calculated electric potential of the dipole, and in the denominator we have r squared. Okay, so the idea here is that any random charge distribution, depending on how accurate you want to calculate potential at large distances, can be approximated different ways. Okay, so the first and leading term is just looking at the total charge, and then 1 over 4 pi epsilon 0 q by r. This is the first term. Okay, this is, I would say, the most crude approximation if you want to make. Okay, and of course that might be okay if you are really, really far from this charge distribution. You don't care about the details. You just look at how much charge is in this volume. Okay. If you want to go one more step, make it a little more accurate, you look at this and you imagine that there's net charge of Q, but there's also some dipole included here. Okay, so you include a term like R hat dot P. P is a dipole moment calculated by this equation. Okay, so this is the dipole moment that you can assume that a random charge distribution has following this equation. And the second term is actually a term that has a form of a dipole potential. And of course, if you go look at the higher terms, you're going to look at the term that looks like the potential of a quadrupole. And the next term is going to be a term that looks like the potential of octupole. Okay, those terms, we are not going into details of those, but I want you to have this conceptual understanding that a random charge distribution can be first approximated as a point charge sitting there. If you want to go one more step, make it more accurate, you can assume that this is made of net charge plus some dipoles included here, and so on. Sounds good? Any question? Is it more or less clear? Or you want me to have more explanation of what we did and why we did?
Part of me wants to say yes to both.
Yes, both of them? Okay,
Part of it is very clear to me, and then the other part is I feel like I need more explanation, but I'm not sure where.
Okay, so more explanation on the conceptual part of why we did this? Or on the steps that we did this?
Definitely more on the conceptual part.
On the conceptual, okay. So here is a basic idea. Okay, let's start from beginning. Forget about the details. Imagine this. Imagine you have a random charge distribution. Okay, and imagine you are in a situation that you are looking at this charge distribution from very far distance. Okay, so one way to calculate potential is doing actually this integral in a very precise way. Okay, so now doing that integral is difficult, a lot of times not even possible. Okay, but if you are really looking at this charge distribution from far distances, it's not even useful to calculate this integral accurately. Okay, there are approximate ways. And what we are doing here is looking at what type of approximation we can have, considering that we are far away from the charge distribution. Okay, so now conceptually there's one way. Okay, so imagine I look at certain charge distribution here from far distances. Sometimes I don't even need to care what is the details of this charge distribution and how the charges is different at different points. Okay, so sometimes what I only need to care is that what is the total charge here. Okay, and imagine that as one point charge. Okay, and calculate potential. And this is what you get here in the leading term. Okay, so the total charge divided by R. If you look at this, this is basically a point charge potential. Okay, and that's how we can calculate. Okay, so this is the most crude way. Okay, but there is ways that we can make it a little more accurate. Okay, so the next step, what we can do is that we can make the assumption that the whole charge distribution is, of course, it carries some net charge, which is Q here, but because of the randomness and all the details of the distribution, we can assume that it's made of that net charge as well as some dipoles. Okay, so those dipoles make it a little more accurate, and then we can calculate a second term, which is very similar in the format, very similar to the potential of a dipole. Okay, R dot P divided by R squared. This is R squared is how it decreases the same way that the dipole potential decreases, and P, the dipole moment, can be calculated based on this. Okay, So you can imagine if you have really one single point charge here, the dipole term just vanishes, it just becomes zero. Okay. So then if you want to include more terms, the other terms, this is going to be whatever it is, it's going to be proportional to 1 over r cubed. The next one are going to be proportional to 1 over r to the power of 4, and so on. These terms are smaller and smaller. If you want to include more terms, you are making it more and more accurate. But of course, these terms are smaller and smaller. Sometimes we can stop here and not even worry about the rest. Okay. So the concept here is how you can approximate potential of a random charge distribution at large distances. And these terms are the steps that you can take to calculate this, make it accurate, make it more and more accurate. Did that help?
Yeah, that helped a bit.
Okay. Yeah, of course, I again encourage you to read your textbook as well. Okay, that might give you a different perspective. Sounds good. Any question? Any question on the steps that you took here? Good. Okay, so with this, I believe we completed chapter 3. Yes, and then I can start discussion on chapter 4. I'm not going to teach much, but I'm going to give you the basic idea about electric field in maths. Sounds good? Okay, so let me get to the stuff on the board. Okay, so in chapter 4, what we study is basically this. Imagine you have electric fields. Here I draw some very basic parallel uniform electric field. I'm going to call it zero. Okay. So the idea is that you have electric field in a space, and then you put a dielectric material inside the electric field. Okay. You put the dielectric material inside the electric field. The question is first, what happens to this material? Because you have electric field, and that electric field exerts force on all the small electron and protons inside the material. Okay, so what happens to that? And eventually we want to calculate what kind of electric field we will have inside this. Okay, so the quick answer is that if the electric field outside is E naught, inside we will get some electric field, okay, which is different from Epstein naught. Okay, and a lot of times this electric field is in the same direction, but in terms of the magnitude, is smaller than E naught. So it's non-zero. You get some electric field, unlike conductors that we used to get no electric field inside. For dielectric materials, we will get some electric field inside. Okay, and another answer, quick answer, is that all the materials inside, they get polarized. Okay, so what does it mean if it's, I say it gets polarized? That means that we can have dipoles inside that are aligned in the same direction of the electric field. Okay, so you have this piece of material, you put it inside the electric field, okay? Before that, the material is not polarized at all. Okay, they don't have any polarization. There is no negative positive charges aligned in a certain direction. But as soon as you put this inside that electric field, you get polarization inside. Okay, so what we're gonna do in this chapter, we're gonna first look at this polarization, And then we want to mathematically formulate what it means by polarization and what kind of effect that polarization has on the electric field inside matter. And then eventually the question is what actually electric field you get inside. Because as I said, the electric field inside is not going to be equal to the electric field outside. Okay, so what happens? So first let's talk about the polarization. Okay, so a lot of materials are made of molecules, and those molecules are polarized molecules. Okay, so if you want to think about that, you can imagine each single molecule is like a dipole. Okay, so now let's imagine this marker in my hand. Probably it's made of dipoles. Okay, that means there are a lot of molecules that are polar molecules inside this. So does it have any net electric charge? No, it doesn't, because it has all these positive and negative charges basically canceling out each other. Okay. Is it polarized? That means my question is that are all these polar negative positive charges aligned in one direction? The answer is no. They are just randomly distributed, and their direction is completely random. So any electric field arising from one of these dipoles is sort of canceled out by others. So as a whole, this marker in my hand is not creating any electric field. Okay. But now, if I put this marker inside a very strong electric field, what happens is that all these random dipoles kind of get aligned in one direction, dictated by the direction of the electric field. Okay. So when that happens, then this marker as a whole, okay, will create some electric field. Okay, and the materials inside make electric. Okay, so now you can imagine that this dielectric, okay, is made of a large number of little dipoles. Okay, so that happens when you have polar molecules. Now you may ask a question: what if we have a material which is very pure and made of just atoms, and atoms are not polar? Okay, you can have materials made of non-polar atoms. You can have gas from hydrogen and so on. What happens to those type of materials when we put them inside electric field? Okay, it turns out even if one atom is not polarized, if you put that inside electric field strong enough, you can polarize atoms. Okay, so polarization of each atom, in fact, can be calculated, approximated linearly based on what electric fields you have. Okay, so without electric field, atoms are not polarized. But if you put the same atoms inside an electric field, you get certain polarization. Okay, so if you want to do it very accurately, you really need to look at the quantum mechanics of that. That's beyond the scope of the discussion here. But your textbook has a nice description that if you even model the atom in a very primitive, simple, mechanistic way, which is one positive charge in the center, kind of surrounded by a cloud of negative charges, even such system, if you put it inside an electric field, you're going to polarize it. You're going to push the positive charge to this side, okay? So there's going to be a bit of dislocation, relative dislocation of the positive and negative charges, and the whole thing that was non-polar and that was neutral gets polarized a little bit. Okay, it still stays neutral. The positive and negative charges don't change magnitude. If you add up all the positive and negative charges, they are zero, but you get a little bit of polarization, and that is proportional to how much electric field you are applying on the system. Okay, so as a whole, you can put some material like this inside electric field. The material is not polarized at all, but as long as it goes inside the electric field, depending on the strength of the electric field, you get polarization. Okay, the stronger the electric field, the stronger the polarization you get. Okay, and in fact, you can calculate for things like a dipole. Okay, imagine it's a dipole made of negative and positive charge. If you negative and positive charge, if you put this dipole inside electric field, you will have forces like this. a force which is QE. On this direction, a force like negative QE on the negative side, and as a whole, what you're doing is that the electric field is trying to align this dipole in the direction of the electric field. Okay, and if you calculate the torque that this electric field is exerting on the dipole is Q times E times D, if the D is the distance. If D is the distance, and this is basically P cross E. Okay. Something like this. Okay. It should be the other way. Q E cross E. So the electric field puts some torque on the dipole to make that dipole get aligned in the direction of the electric. Okay. So in summary, whether your material is made of dipoles or made of neutral atoms, what happens? You put them in electric field, each particle inside the material gets polarized, and if it was dipole, the dipole is kind of aligned in the direction of the electric field. Now you may ask, are all the dipoles in the material are getting aligned in the direction of the electric field? I would say no, not all of them, because all of these have thermal energy as well. They don't like to get aligned. They want to move around and they want to have all the direction possible. But as long as there's a force on them, okay, some of them get aligned, okay? And the stronger the electric field, the more dipole you're aligning in the direction of the electric field. Of course, temperature is important. If you take the statistical physics course, then there are ways to calculate. Depending on the temperature, you will have more and more. So if you lower the temperature, you're going to get more and more dipole aligned in the direction of electric field. And if you increase the temperature, you're going to get less and less, because that thermal energy gives just random duration to these dipoles. Okay. So with this discussion, I don't have much time. So it was just a brief introduction to chapter 4 that I will basically start the chapter on Tuesday. We start from here and we try to mathematically quantify the dipole moments and we define polarization. And for each small part of the material, we can say there is a dipole moment associated with this and so on. Okay. So for now, I want to stop. Okay, if you have any question, you can ask. And if not, then we will continue on Tuesday.
What does D stand for? Just the distance?
D is a vector from negative charge to positive charge, the distance between negative and positive for the dipole.
Okay.
And this is the beginning
Q
of
times D becomes the dipole moment.
and Professor, this is technically the beginning of chapter.
Can you speak a little louder?
This is technically the beginning of chapter 4, right?
This is the beginning of the chapter. Any question? No? All right, guys. So see you on Tuesday morning. Okay?
Okay, thank you. Bye. Thank you, Professor.
Bye.
Thank you.